Hello class, I would like to go over chapter 6, section 6.1 and 6.2 for today. In chapter 6, you will learn about the modeling random. You will learning about normal model and binomial models. And for normal models, we usually talking about continuous random variables. So, and you will learn discrete and continuous variables in this section to identify and learn how to compute by using StatQuant or TI-84 in section 6.2. Okay. So 6.1, probability distributions are models of random experiments. So in this section, you will learn how to distinguish between discrete and continuous random variables. And what does it mean, probability distribution? In chapter 5, we have learned about theoretical probabilities, right? But in this section, you're learning about probability distribution. We're talking about more advanced, a different type of probabilities. And you will learn using probability distribution to compute probabilities by technologies. Okay. All right, so I'm having, let me see. Okay, let me do 6.1 right here. Okay, so for probability in 6.1, probability distributions, we are talking about tables and graphs because these two types, they display the outcomes and probability of we call the possible outcome of the random experiment from the story. So we're not using table and graph to showing it, but mostly we're going to using the table. And we're going to find the probability of each outcome from, by drawing the table, and then we find all of it. And then question by question, we will answer those. The table looks like this. So this table example talking about rolling a die. And you see right there, the prompt is rolling a die, but they, in the question, they asking one of the question only. So usually they have more than one question, but here they given us the question is, what is the probability of rolling a 5 or a 6? You're learning about how to compute theoretical probability by using the word or and conditional probability, right? But in this case, we're not talking about conditional probability. We're talking about like the probability like normally that we compute theoretical probability like regular probability, not conditional probability. And when they do experiment rolling a dice, then you can imagine that all possible outcomes can be probability of a 1, probability of a 2, a 3, a 4, a 5, and a 6 individually, right? Because a dice have 6 faces. So from 1 to 6. And each possible outcome for each number, for each face, is only 1 out of 6 only, because you cannot, like you rolling it cannot come up 1 and 2 at the same time. Agree? So every time that you're rolling a die, one time, then the face that you can observe is just one number, one value, and each value, the probability only 1 out of 6. You can do experiment by yourself by having a dice and rolling it, and you can recall all of it. you're not going to count like how many one is landing on and you add all the probably you're not going to do like that. That is for the probability that you do like the observation that we have learned in chapter 5 section 5.1, right? But this is different case. You just list out all the possible outcome. So for when we're talking about rolling a dice and all the possible outcome that we are having, let me annotate here. Or the sample space. So when we're talking about rolling a dice one time, the sample space for this case will be a set of a 1, or 2, or 3, or 4, or 5, and a 6 only, right? They keep landing on this value. So you're not going to take probability of like combined number at all. No, you don't do that. For each of this possible outcome, okay, the probability of a 1, so they wrote X. So this can consider X inside the box here. X is 1, X is 2, X is 3, X is 4, and so on. And P of X, which is probability of each value in this sample space. So probability of landing on 1 is 1 out of 6. Probability of landing on 2 is 1 out of 6, and so on, right? If we're rolling a dice one time. And that's happened. Okay, and they make the table for us. The reason they make the table for us because they want us to compute P of X easier, you know, like you can see by eyes, you can compute that, and you got a value. The purpose of this and the rule is for the probability distribution for this case is they have to add up all of this, add together, give you value is 1. 1 stands for 100%. Or you have each of this add together, you got 6 out of 6, right? 6 out of 6, which is 1. It have to add up the sum to 1. All right. So every single case like this, we're talking about probability distribution. Rather, you testing it by yourself to make sure that you add the probability of value of X correctly. They have to add up to 1. That maximum is 1. So that you can make sure that, okay, you are doing the probability distribution on the right track. And to answer the question, they're asking, what is the probability of rolling a 5 or a 6? All right, so let me write it down. Let's see. The probability that you're rolling a 5 or a 6. You have known the formula already, isn't it? So if rolling a 5 or a 6, 5 and 6, what do you think? Are they independent? They are, right? They're not joined together. They not like have something to join together. So they are independent in this case. And what you're gonna do is you got probability of a 5, you add with probability of a 6. You not subtract anything. You not subtract the join part because these two separate. So the answer for this will be P of 5 that you can see is 1 out of 6. You add with P of 6 is 1 out of 6, give you 2 out of 6, which is 1/3, right? So on the test, you make sure that you give me this steps and then decimal value. So this gives us 0.333, right? So on. So 3 repeating it. You box for me. But you need to show your work like this on your test. All right, if you have any question, please again let me know. So let me move on. Here is the graph. They're showing another model. So for the graph, so this graph represent for look like discrete random variable. So you can graph like this way. What does it mean? It means for each probability, you see that they did converting it, right? They convert that value from 0 to 0 0.1, 0 0.2, 0 0.3, and so on. And they having the number of, right here they're talking about, let me see, the number of the book. They had different story right now. So we can do similar with the dice, just similarly. For here, they are having a graph for us about rating a book. Okay, so estimate the probability that a randomly selected reviewer gave this book a 3-star rating. So 3-star rating, based on this, you can see how many probability? About 0.1, which means 10%. By looking at a graph, then you can tell the probability of each possible outcome, which is in this case is 1, 2, 3, 4, 5, right? It's like that. And from the graph, actually, I'm not asking you to convert from the graph into the table, but if you want to do so, it's going to be like this. So X value can be 1, 2, 3, 4, 5. 1, 2, 3, 4, and 5 stars. So 1 is like around, you can estimate it at the end. 2 is at the end too, because it's not really like clearly showing us to see it. But however, you have to make sure all PX add together have to be 1. So now I can see obviously is 3 is 10%, or which is 0.1 or 1 out of 10, right? Or 0.1 for 3, 0.1. And 4, what does it mean 4? Two point something, 0.2 something, right? So let me estimate is 0.2, 0.25 right here, 0.23. For 4, 0.23. 5 is 0.1. 0.6. See that? And so 1 you can estimate from here to here is you can estimate by 0.03 for 1. And 2 is maybe 0.05. Make sure that we're going to add all of this together, give us a 1. So let's make that become 0.02. So we're going to get calculator. Let me try to add this all up. Does this make up to 1? Yeah. But looking at the graph, then it's not really accurate by eyes, right? But let me try 0.02 plus 0.05 plus 0.1 plus 0.23 plus 0.6. Perfect. Okay, perfect. Yes. So we add all of this up together, give us a 1. So this is the sum. This is notation for summation. The sum of P of X equal to 1, which mean, let me separate that into more detail. P of X. Okay. So X, you start from number 1. Maximum is number 5. It means you are having P of 1 plus P of 2 plus P of 3 plus P of 4 plus P of 5. And then you replace the value of the P of X together, or together add up. It should be a 1 to make this become probability distributions. So that's how you're testing before you compute the probability. Okay. So some question might be like, okay, what is the probability of the reviewer gave this book 2 star and up, for example, like that. The question, I'm just making up, probability of the viewer grading 2 star and up, which means at least 2 star, right? So based on the table or the graph, then you can see 2 star and up. I'm going to change different color. I'm going to get out of this, right? Out of this value. Another word, out of this value. So if you take time to add all of this up, it takes more time, right? So you rather using complement rules, which is 1 minus probability of 1, right? Or x equal to 1. Then you're going to have 1 minus 0.02. This gives you a value, right? So you take 1 minus of that will give us 0.98. And another question might be asking, so what is the probability that the reviewer gave this book more than 3 stars? The probability of the book give this the probability of x greater than 3, more than 3 stars. And what do we do? Which means more than 3 would just count from 4 to 5 only, right? That means you need to find probability of 4 star plus probability of 5 star. So what do you have? So that's equal to 0.23 plus 0.6. This add up give us 0.83, right? And you're done. That's how you do this probability distribution, by looking at graph and tables. So every time that in this case, then that's the way that you're doing it. All right. All right, class. You have any question? Please let me know. Okay, let's move on. We do have 2 types of numerical variables. We have 2 types. Remember in chapter 1, you're learning about categorical and numerical variables, right? So for this section, in numerical variables, you are having 2 sub variables. We call discrete numerical value or discrete numerical data, and we do have continuous data, continuous random variables, right? So for discrete, we're talking about specific number, like it's not changing, it's not like continuous. But for the different type, like continuous, it's changing like very small number, very small details. It's changing by time or changing by something. Example, for discrete, we have number of your siblings. Right away, for example, number of my siblings, we have 3. Then obviously it's 3. It's not changing, like number of songs that you like, right? Number of songs on an MP3 player. It's like, it's obvious value, like number counting. And for continuous outcomes cannot be listed or counted because they occur over a range of a value, right? So for example, your current grade, right? Your current grade right now is like, for example, 4 point, like an A. But then when you take, but the class is not end yet. So we are having tests and homework coming up, then your grade might change or keep the same, right? So they are continuous. The height of the basketball players or a weight of the sandwich, because you cannot like count those. So they are continuous. For the continuous outcome, the probability that you will find or you will learn how to compute, we're going to use by StatQuant. So this continuous have to use StatQuant. RTI 84. And for the continuous random variable, we're going to focus on the shape like this, bell shape. For discrete numerical random variable that you just do, that we just have done it, right? We find the probability distributions, like using tables and stuff like that. Discrete or continuous. So here is telling us how to identify if a variable is discrete or continuous. So let's try. Number of cars owned by a household is obviously like how many cars that you own. This is discrete. Number of pets owned by a student is obviously like the number of pets, right? You can count how many pets, discrete. The time that it takes a worker to commute to a job site. So this is like you cannot count. You cannot count the time. You're just recording the time, but not counting the time, right? Or the height of the building in the downtown San Francisco. So there's 2, 3, and 4. They are example of the continuous. So all P of X value must be between 0 and 1 only. And the sum of all Px have to add up to 1. So that's the rule. Creating a probability distribution. This is a difficult story. So this one we have to analyze a bit more. It's not obvious, like I just gave you an example about a dice or about coin, right? So this is kind of a bit more tricky. So this example require you to know how to interpret more before you draw the table. So let me demonstrate for you to see it. Move up. Suppose you roll a fair 6-sided die. Right? You imagine that now it's talking about dice, but this case they're talking about game using a dice, right? Okay, you win $10 if you roll a 5 or a 6. You will lose $5 if you roll a 1. And for any other outcomes, which is roll a 2, 3, 4, 2, 3, 4, right? Then you win or lose nothing, which means you win or lose nothing is a 0. So they want us to create a table and showing this and showing the probability distribution of each outcome for the amount of the money you win that when you're playing this game. So first analyze this. You got a fair dice, right? And you already have the sample space is 1, 2, 3, 4, 5, and 6. Right. So now they said talking about something deeper. You win $10. You win $10, which is you add $10 in your pocket, right? You win it. you win $10 when you roll a dice of 5 or 6. Then you win. And you lose $5 when you roll 1. You lose $5 when you roll number 1. And any other outcome, you lose or win nothing, which is a 0. You roll, which means you roll a 2, 3, and a 4, right? So first you need to analyze like this before you jump to. So now you have to identify, so what is my X in this case? Is it 1, 2, 3, 4, 5, 6? Or is it talking about my money, right? So in the story, they want us to focusing on the win or losing things. They want us to create a table showing the distribution for the money, for the amount of the money. So in this case, X will be the amount of the money that you win or you lose in this case. That's your X. And your job, we have to figure out P of X, which is P of the plus 10, P of minus 5, P of the 0 in this case. Okay. Right here. So here there are 3 possible outcomes that we see. Win $10, lose $5, or win or lose nothing. And we have X will be 10 minus 5 or a 0. So the probability of rolling so now here it just, we're not making a table yet, right? They analyzing it for us to see it. And next step is they want to find the probability of each of X, which is they want to find P of when X win $10, right? X is $10. Another word, P of when you roll a 5 or 6. That's what they're asking. Secondly, they want us to find P of when X is minus 5, which means when you're rolling a 1, right, equal 3 P of 0, X is 0, is mean when you rolling 2, 3, or 4. So this is the case. So now later we're going to make the table for this case. Now we would like to find each probability of 1, 2, and step 1, 2, and 3 first, and then we can make the table later. So the probability of rolling a 5 or 6, that means like I did an example earlier. We got P of 5 is 1 out of 6. Each of the face of the dice have probability is 1 out of 6. So we got a 5 or 6, which is 1 plus 6, or 1 over 6 plus 1 over 6, give us 2 out of 6, or 1/3, right? And probability of rolling a 1 give us just one outcome, which is 1 out of 6. But when you lose or win nothing for rolling a 2 or 3 or 4, again, you want to add all of this together, right? So this means P over 2, P of 3, plus P of 4, you not subtract because they are all independent. So you got 1, 6, plus 1, 6, plus 1, 6. This is 3 out of 6. Yeah, again, if you have any question, please let me know. So here's the table that they have made for us. That they are rearranging it from small to higher value. So, and make sure all px add together have to be 1, right? 1, 6 plus 3, 6 plus 2, 6, or 6 out of 6, which is 1. So that is for the probability for the discrete random variable. But how about the continuous random variable? Like I introduced you earlier, we have to using the bell shape to compute because we really cannot count those, right? So the graph for all of this is it looks like this. It looks like this. Look like this. So here is, it's not really a bell shape yet, right? However, you will learn later. So here is the demonstration for the example about the waiting times or for waiting for the bus, maybe. So this probability density curve show the probability of wait times before service at a coffee shop. The shaded area represents the probability of a wait time between 0 and 2 minutes. Right? You can see that. So the total area under the curve is equal to 1. Right? And this model is uniform, is again, this graph represents for continuous random variables and is more obvious than the density one. So here is again is the waiting time, and you see that the flat here is not changing. It's saying that you're waiting the same time, right? Each time that you just give you the same. So this one look like the rectangle, so you can easier compute, you know, like the area here. The other one on the top, you need to use the calculus to involving it. This one you don't have to. This one you can using just the formula for by adding up all of this, like constantly. Oh, well, it's not moving. A bus arrives at a certain stop every 12 minutes, and the graph shows the probability distribution for wait times before the bus arrives. Use the distribution to find the probability of the wait time between 4 and 10 minutes. So to do that, we have to like estimate, for example, 4 is right here. Right, we're going to compute this area in this box. Okay, right here. So they shaded for us, and in order to compute that, you can using the algebra to do it by having the area, multiply them by length and the height, and you have the value. So the purpose out of this showing us we finding the area under the curve, especially for the shape, for the bell shape, we call normal distribution. In general, finding area under the curve that are not geometric shapes like rectangle is difficult and require using some type of the technology, computer technology, which is StatQuant, that in section 6.2 will showing us. I will run some StatQuant for you to see that as well. Okay, so this is again, they introduce just like the objective that you will focusing on in 6.2. So the normal model. So one of the most widely used probability models for continuous numerical random variables we call the bell shape, or we call normal distribution. That's a different name. Good. Let me scroll down like that. So the more data, the more the bell shape going to be shrink perfectly. So here is an example about normal model, which is applied for all continuous random variables. So this was histogram, which is histogram here. The red curve, which is just shaded along to see how data shrink into that bell shape, so that we can easier compute the area under the curve in this case. So for here, we are having the symmetric and unimodel, which is only one top here. Right? So we have only one with unimodel. So can be modeled by using the normal distribution. For normal distribution, actually, if we compute by hands, it requires more techniques. But because we are using StatQuants mostly, the easiest way is you need to identify all the x value, all the mean in the case, and all the standard deviation in the case, and you have to understand the keyword so that to find the probability, like on the left side or on the right side of the bell shape. However, again, no worry, because I will demonstrate for you to see it easily, and it's very easy to compute and figure out the probabilities for a continuous situation like this. We got two graphs in front of you, the blue and the red one. The red graph showing you the standard deviation is very small, right? Which is your data is like shrink together. And the blue color given us the larger standard deviations, it's more spread out. Okay, it's more spread out. So if we have these two normal, they are still called normal distribution. They still call bell shape, okay? But it's not like a standard one. It's not like the standard curve. The standard curve is look like all the curve, the area, the standard curve is like, it look like more a bell. So here is just describing the standard deviation for these two graphs is different. And the normal distribution, we have the following right down here. We still call this is normal, okay? We still call it is normal, but we're not, I'm not saying that it's a standard. It's not a standard normal distribution. It's not a standard normal distribution. That's what I mean. So out of this graph, we call normal distribution. It looks like a bell shape. Even it's big, tall, wide, or narrow, they still call normal distribution. So for all of this, you can notice for women and men, they have look like the bell shape is the same, but look like they're having different data, right? This normal curve shows the distribution of the height for adult men and women in the US. We notice that the spread of each curve is look like the same, but where they having the mean is different. So what happened? So they give us some new notation for if we're talking about two group, men and women like that. So we're gonna have two mean and two standard deviation. Notation for mean, this we call mu here, like that you wrote like that, called mu. to represent the mean of this probability. Okay, so if we're talking about mean for women, you might write mu1 or mu number 1 if they talk women first. And sigma is the sample represent for the standard deviation. The fancy name for this is population standard deviations. This standard deviation is more like talking about more bigger group compared to the one that you learn in chapter 1 or chapter 2, we call S. This is we call sample standard deviation. So this we call population standard deviation. Similarly with mu, this we call population mean. And the mean that you learn in chapter 1 or chapter 2 is X bar. This is called sample standard, sample mean. Usually X bar is talking about a small group. So if we're talking about, if we want to estimate the bigger group, the mean for bigger group, we base on X bar, right? Similarly for S, small s. We have the formula how to compute this already. You can check back, okay? But for the from chapter 6 and so on, you will see they already have, they will provide for us. They already compute that for us already. So you don't have to compute, you just know how to recognize, and so that you can enter in your StatCrunch. And n parentheses, mu, comma, sigma, parentheses, this represent for normal distribution, okay? They all the time given us mu and the standard deviation to in the story. So here they introduce us using technology to compute is faster, easier, and more accurate. They give us picture, they give us data that we want. And here is for people using TI-84 calculator. And this is the steps. Just follow the step, you got it. Okay, and for the example like that, and we're using TI-84, you compute all of this in step by step like this. Let me show you. Here's just a picture, right? Using TI-84, we're gonna find normal on the calculator. You got the step like this. Let me see. This is StatCrunch. Okay. So the step for TI-84 is like this. Oh yeah. Okay, and then you enter all the data in they given you. We got a probability will be 0.589. Similarly with StatCrunch, but we're using like different steps. So I'm gonna try to run StatCrunch for now. They have, let me see, mean that you recognize before you run StatCrunch when you do your test. Your mean is 29.5 inches, your standard deviation 2.5, and they want us to find the probability that the randomly selected harbor seal pup is longer. The keyword is longer, right? Longer than 31 inches. In StatCrunch, even though you write greater than or equal to, it's just the same, give you the same value, okay? And we are having that point out already out of this, and you run StatCrunch. Let me try to run it for you to see it. Open it. Open StatQuant. How? Okay, I go to my stat lab. Okay. StatQuant.com. And you log in. So, okay, so I go to stat, calculators, binomial, normal, learning binomial distribution. You're having this table pop up. This is just a standard model. We have the standard one, right? And we have between. When you finding the probability that in the between of something to something, then you're going to use it. You're going to use between. Okay. Otherwise, you're using standard one because we're talking about longer. You see that here? Less than or equal to mean shorter, right? Shorter than or less than, or like the word that will be similarly describing when you're using the word less than, then you're using this. At most, and yeah, another word for this will be at most. So in the case that we are having, we found a mean. We not do between, right? We do on the one side, left, either left or right side. Mean is, I remember, is 29.5. Standard deviation is, I remember, is 2.5. And here is longer. So you click on that and you switch to greater than. And this will be, I think 31, right? Let's compute to see what happened. So here we are having when you click compute, you got the probability that COPUB is like longer than something, right? It's a story. So we are having, you click 31 there, you found the probability is 0.274, blah, blah, blah. But make sure you route to 110, which means that you see the 4 right there is smaller than 5. It means you keep 0.27, which is 27% for this case. On the test, what I want you to do is you copy this picture, right? And copy and paste on your test. I can see all the mean, standard deviation, how are you using this, and the probability in the picture like this on your test. Okay, in order to copy it, you see the word, the option right there. You can copy it or save, right? Print or download or something. If you copy and paste and just click copy and paste to document, you're done. So it's 0.27. So let's go back to the lecture to see if it's matching. 31, okay. StatQuant using this. Similar, right? There you go. Got the same, exactly the same value. So we did correctly. So I would like you to write down to make it more formal, like this for me. You box it. You got the shape like that, and then you write like this. P of x greater or equal to 31 equal to 0.274. Like I want you to write in 2 decimal places, it will be 2.7. 0.27. With that technology, I will teach you directly in class about this. For this, I prefer to using StatQuant. Just have picture. You don't have to draw by hands. Let's see. So no worry about this. When you compute by hand, there's more steps to do, which means you have to find z-score first, and then convert everything mu into a 0, stuff like that. So for the face-to-face class, I would like to go over this in more details. But again, like I say, usually we're using technologies, so I prefer you to using StatQuants mostly. They show the same step, but extra work will be finding z and then using the table to looking at the data. Okay. So normal, well, or inverse normal. So which means they want us to find the opposite, right? The opposite. So in order to do that, for example, they are having the following. It's known that the height of the adult man follow a normal model. For each of the following situations, decide if it's a normal or inverse normal problem. So an example, a clothing store manager wonder what percent of her customer are taller than 6 feet. So here, the reason they're talking about inverse normal is like this. You got a bell shape, right? So here is the x value. Usually we have x value, we have mean, right? We have standard deviation and everything, and you find the probability. So now they're giving you a probability, I think. I mean, okay. What percent of her customer are the taller than 6 feet, right? So if they given you the probability, then it will be they want us to find backward. So this is demonstrate for number 1. This is number 1 picture. That means you find a probability who taller than 6 feet. So let me say taller than 6 feet. Then you find the probability taller than 6 feet will be on the right side. Like this, you find this. So this is P of x greater or equal to 6 feet. Okay, that's for demonstrate for number 1. Demonstrate for number 2. They give you the data is what? This is mu. %20 of the man, okay, cater to the tallest of men and want to know what is the height she should accommodate. So they given you the probability. They given you the probability already. They given you this. Okay, given 20%. Your job, you have to know where is the height, the x value right here, question mark. That's what we call inverse. Okay. All right, let me see. Is it 6.2 is done? Yeah, okay. But no worry about much on that. So what I want you to focus on, that I just demonstrate the StatQuant for you to compute. That's what I want you to practice on more. Right? So that is 6.1 and 6.2. If you have any question, please let me know. I believe I did record 6.3. Let me double check. Yes, I do record it. All right, class, you have any question, please again let me know. Stop recording. See you next time.